last one, talk about how to visualize the distribution underlying the data. So there are several methods people have developed, types of plots, let's say histogram, box whisker, violin plots, and scatter plots give you a pretty good idea of how a data set that you're looking at is distributed. Now, histograms are probably the most commonly used tool, and it's easy to do. You just define bins and count the number of data points that fall into each bin, and then you plot on a chart how tall the number of points are, how many points are in each bin. So it gives you a representation of the probability density function underlying that data. Really, the subjective thing about the histogram is that there is no real set way or objective way to select the number of bins. So if you pick too few bins, you don't get any idea what the distribution is. If you pick too many, you get mostly ones and twos with some blanks, and it doesn't give you an idea what the distribution is. There are some rules that people have come up with to try as a starting point for a number of bins. Square root of n, log of n plus 1, 2 times the cube root of n. They'll give you some idea of a good starting point, but really it's best to just try different numbers of bins until you find one that seems to sort of focus in on the data, let's say. And one of the nice things that you can do if you have enough data with a with a histogram plot is you can compute an empirical PDF from that. So recalling that the PDF integrates to 1, you can calculate the area under the histogram and then divide each bin value by that. And that's very easy to do if all the bins have constant width. It's just the number of bins times the number of points times the bin width. And you see on the plots, this is number of occurrences on the left, and then PDF on the right. If you summed all of those up, it would sum up to 1. In this case, it would be pretty safe to assume that's normally distributed. And then once you have a PDF, or your histogram on a PDF scale, you can plot PDF functions over that to compare two different distributions. Now, another way that people sometimes visualize data measurements would be box whisker or violin plots. And so these are just taking, say, 5 numbers out of your distribution: the max, the min, the 25% quartile, 75% quartile, and the mean or the median, and making one or the other type of plot from those 5 pieces of information. And then you see on the plot like 25% here, 75% here. So all of them give you an idea of what that interquartile range is, and where the median falls. So you can see if it's skewed, if the median was, say, all the way down here, that kind of thing. And then these whiskers extend off typically to 1.5 times the interquartile range in each direction. For box whisker plots, you can see the outliers. Anything that falls outside of this lower fence or upper fence is plotted as an outlier, so you can see if there is data outside of those typical ranges. And it gives you an idea of whether you have outliers in your data. The violin plots have a representation of the PDF. It's symmetric. It's the same on each side, but that gives you an idea of what the PDF of the data look like, which you can't get from the box whisker plots. So these are sort of boiled down, but they're nice for when you have multiple pieces of data that you want to compare to each other. So just for reference, or to give some illustration of that, I took the year 1 year's worth of temperatures for Jacksonville and plotted box whisker plots and violin plots for each month. And you can see from the chart, you can see which months had outliers. You can see, there's only one day over 100 looking box whisker plot. And the violin plots, you can see months where you can just get any temperature any day, which is kind of almost uniform distributions, or it's a really small distribution of hot temperatures, that kind of thing. So individual outliers, you can see them on box whisker. The densities you can see on the violin plots. I'll move on to scatter plots. This is useful when you have multiple dimensions to the data, or you want to see if an output variable is related, shows a strong relationship to one of your input variables. So we have this function here, and then we have the y value plotted against the x value and a correlation coefficient computed for each of those. You can see that the y has a strong relationship between x1 and x2, but this coefficient in front of x3 was just too small, and the correlation is really low. Also, you can see for positive correlation, as x increases, the y is increasing, and as negative correlation tells you that if x2 increases, y2 is decreasing. Be careful in assumptions about this correlation coefficient, Pearson correlation coefficient. It will only tell you if there's a linear correlation between the two sets of data. If there is a strong nonlinear correlation, then you'll get a Pearson correlation coefficient really close to zero, plotted here. But sometimes you do have data that are correlated and strongly correlated. So one of the most famous examples of that was a set of data taken by Verkler back in 1979. What he did was he started crack growths at he gave them a starting size, 9 millimeters, and he applied the same constant amplitude load to all of the samples of 2024 Luna, and got all of these different crack growth curves. If you take this and you boil it down and calculate the Paris fits to each crack growth curve, you get the intercept and the exponent, and plot those together, you'll get what we're showing here. And you can see that if you change the value of your intercept, then you get a different range for where the exponent will fall from this set of data. So that's indicating that the Paris intercept was strongly correlated with the Paris exponent. So in order to simulate this kind of correlation, you would need to use a joint distribution for these two values. So for uncorrelated variables, you can just make the joint PDF by multiplying the PDFs of the two variables together. But that doesn't work when they're correlated. Generally, if the variables are correlated and they're not normally distributed, then you have to, the PDF function doesn't reduce to a function of the individual random variables. You have to calculate the PDF function given a combination of the two variables together. If they are normal or can be transformed to normal, then you can use a multivariate normal distribution, which we showed just for reference what the matrix function of that distribution would look like. But then you can easily simulate these. So last slide, last note. I put together some simulations of crack growth using uncorrelated and correlated Paris coefficients, and to compare to this set of Verkler data. You can see that if you ignore the correlation, and both of these simulations use the same starting uniform random numbers. If you ignore the correlation, almost half of these or more fail before the first sample that fails in the data. But if you do include the correlation, then you get essentially the same spread, the same uncertainty in the output as you had in the original data. So that would be. Excellent. Yeah. Any questions? We can move on